All right, let's start off strong on number one. Let's walk you through the process. If you struggled on this, it's okay. You probably haven't had to do one in a while. Okay, well, let's talk about how to do it, and it's going to give us a nice kind of fundamental basis for the transformers, since some of the calculation is Ohm's law related, like these are. This says when run in parallel using two conduits. Okay, that's a very important note right off the bat. Blank Casey mill is the minimum size permitted for conductors run between a generator and a distribution panel board. The generator is 480 volt, three-phase rated at 500 kVA. So right off the bat, when we have those two parallels, remember we're going to get a calculation down to an amount of amperes, and we're going to cut it in half. Okay, we're going to have to split it in two because we have two parallel conduits. So to figure out what size it is, I'm just going to do a little bit of Ohm's law style math. You remember that? It's probably been a minute, but we're going to take the size of that generator, 500,000, and we are going to divide that by our voltage. And since we are in three-phase, we must use that 1.732. Remember him? You remember him? You didn't forget about him, did you? I'd hate for you to forget about that. So we'll do 500,000, and then I'm going to divide by, I'm going to open a parenthesis up. I'm going to do 480 times 1.732, since we are in three-phase. Okay, your square root of 3, right? Remember? And then I'm going to hit equals. And I need a conductor at base level that's good for 601 amps. But there's a caveat since we're talking about generators. And this is that one I showed you. I want to say it's 445.13. Let's go take a quick peek at that. 445 is your article for generators. And 13 is going to be the ampacity of conductors. And inside of this, it says general here, the ampacity of conductors from the generator output terminals to the first distribution device containing an overcurrent protection shall not be less than 115% of the nameplate current rating of the generator. Okay, so we have to do one more little thing. We have to take that 601 and multiply it by 1.15. Okay, so I just left that up on my calculator. So I'm going to multiply that by 1.15. 691 amps-ish. 691.63 as you can see there on the screen. Now, that includes our 115%. That's our 480 volt three-phase based on that 500 kVA generator. Now lastly, what I got to do, since I have two parallel conduits here, is I'm just going to divide that by 2. Divide it by 2. Okay, I'm leaving it all up on the calculator. Divided by 2. So in each conduit that I have there, I need a conductor that is good for 345.8 amps. 0.8 amps. You with me? Don't fall asleep on this one either. I know it's long. Okay. Once I got that 345.8, I'm going to cruise over to my Holy Grail article 310.16. As per usual, I'm going to be looking in that 75-degree column. Remember the rules of 110.14. And most commonly, you're going to be in this column anyway. 75s are typical for terminations for modern equipment. I'm going to cruise right down that column until I find a conductor that is at least good for 345. A 400 kc mill didn't quite make it, but that 500 kc mill did. Okay, that got us there. So I'm going to have parallel 500s coming out of this generator. Okay, equals number 500. Okay, parallel 500s coming out of that generator. Bingo, bango, bongo. Got me?